I just would like to ensure that please prepare a few sheets of paper for note taking, and make sure that the PIC24 FJ64 GS004 datasheet is with you. Okay, class. I would like to give you an advice. Okay, if you have encountered any problem of the following slides, okay, and you are not sure, okay, please switch on the mic and ask question, because I might miss some of the question that you posted into the in the message column. Okay, and please have a habit, such that that you make sure that you understand every slide I'm going to present after this. And please have a habit, don't have a habit, to have or tonight I'm go home, I watch the video, I will understand, all right or not. So try to save your time, try to understand everything, on the spot. Okay, this is my advice to all of you today. Okay, so if everything okay, just give me a thumbs up. Yeah, recording started. Okay, very good. Okay, I'm going very slow today. Okay, let's revise what we have been went through last round. So first is a watchdog timer. So watchdog timer is very important because it helps your system to reset itself when you come to an infinite loop. The infinite loop might be caused by problem caused by hardware, or probably there are some technical problem in your program. Okay, so watchdog timer is very useful. So there's few ways to enable the watchdog timer, and class, remember, watchdog timer exists in any microcontroller, whether it's a STM32, whether it's ESP32, and so on. Okay, there are two ways to enable the watchdog timer. First is by using software. Just basically, you just putting this instruction equal to 1 means directly you switch on the watchdog timer, or you can enable through the config register. This is at CW1. Okay, so you can enable it by setting FWD-TEN equal to 1. Okay, once it's enabled, automatically the low power clock will be switched on. So this low power clock is run at 31 kilohertz. I hope that you still remember from the slide early. These are the low power RC oscillator. Okay, so this means that this will keep on running. Okay, so by an appropriate setting of these two bits, these two bits in the config register. Okay, so FWPSA by default, is you can set between 1 millisecond and 4 milliseconds, and whereas for these 4 bits you can set between pre-scale, or means reduce the frequency from 1 until 32,768. Let's assume the input is 31 kilohertz, because this is a low power RC circuit is 31 kilohertz. So this means that 31 kilohertz divided by, if I'm using 4 bit, okay, 5 bit is 32, 2 power 5 is 32. So 31 kilohertz divided by 32. If I'm using 128 over here, it means it's 31 kilohertz divided by 32 multiplied by 128. So this means the period is about 132 milliseconds. Okay, if your system run beyond 132 milliseconds, it will reset by itself. So therefore, in order to prevent things to be reset, you need to clear the watchdog timer so that you will count from the time 0 again. So this means that to clear the watchdog timer, you have to run this command. Please reminder, this is the uppercase and uppercase. Okay, so for this example, so I set my my clock to be, my pre-scale to be 32, and I set my post-scaler to be 128. So therefore, my watchdog timer is set at 132 milliseconds. Okay, so let's start the program. Let's imagine the program is to blink an LED which is connected to the RB0. Is switch on, example. So I run for delay for 100 milliseconds. So after 100 milliseconds, 132 minus 100 milliseconds, we still have 32 milliseconds before the system to be reset itself. So I run this again, probably this is just few microseconds. So if there's another delay 100 milliseconds before I call for watchdog reset, okay, so definitely if 32 minus 100, this already exceeded 132 milliseconds. Therefore, the system will reset by itself without going through the clear watchdog timer. So means the system is keep on looping over here, keep on resetting itself. Okay, so in order to prevent the system to be reset itself through watchdog timer, maybe you can reduce it to become 20 milliseconds. Okay, it's within the range of 132 milliseconds. So therefore, after 120 milliseconds, you reach the clear the watchdog timer. So this system will keep on repeating itself, okay, without reset by the watchdog timer. So class, you are the designer, you know very well where to put the clear watchdog timer, and you know very well where which section in your program likely to cause an infinite loop. Okay, is it okay, class? So any question from the floor regarding to watchdog timer? Yes, is it clear? So I need to ensure everyone is clear. It will save your time. I know that you guys are very, very busy. Any questions? If no question, give me a thumbs up. You may switch on your mic if you got question. So any question from the floor? Okay, very good. Okay, let's move on. Okay, so class, you may assign watchdog timer in your design, in your assignment. Okay, although you say, oh, it's impossible, my program stuck in the infinite loop, but you remember, you never know. Okay, so this is watchdog timer is a very, very important features in a microcontroller. Let's move on. So basically, this is just talk about oscillator. There are different type of oscillator, whether it's using external oscillator or internal oscillator. As I told you last round, if you PIC24 allow you, to enable the calendar date time, according to the universal time and according to the date of a calendar, by enabling, by connecting these two pins to 32.768 kilohertz of clock. Okay, remember? So this will ensure that I can have let's say I can set my alarm, ring my alarm at 2 o'clock tomorrow morning. So it can be done by using PIC24 microcontroller. Okay. So basically, in a lot of situations, we are using external oscillator. Okay, but however, the beauty of PIC24, they come with the internal fast RC, FRC. So therefore, we will choose the internal FRC, which is 8 megahertz. Okay, so this means we save our time to construct or additional crystal frequency externally. Okay, so again, it's up to your design, up to your application, whether you need internal or external. So definitely external oscillator, you can have a higher frequency, okay, which is more than 8 megahertz. Okay. So here is some of the example, how we are connect the external oscillator. Okay. Actually, we can boost up the frequency by enabling the PLL. Okay. Still remember this diagram. Okay. So even though we connect the external oscillator, we can increase, the oscillator by the multiplication of 4 by enable the PLL. If I'm putting 8 megahertz here, 4 times 8 megahertz, you might get about 32 megahertz. Okay, there's a lot of choices for you. Okay, but however, again, we are The one we are choosing today is a 8 megahertz, okay, internal FRC. Okay, so when we come to oscillator, there's few special function register is always involved, which are the oscon, clock divide, and ostune. Let's have a look. And class, one more thing I want to make you to remind all of you. Remember, all these devices, all these like oscillator, is still available in other microcontroller. You have to refer their data sheets. It more or less is the same, okay? But however, the special function register used might be different. So after this, I will show you ESP32, okay? And so this is the oscon register. So oscon register is something that is very interesting and very unique. We will go through it in details now. Okay, so let's start with the first one, which is called fail-safe clock monitor. So fail-safe clock monitor basically, okay, to help you to solve the problem when your external oscillator died, malfunction. Okay, it's very big. I mean, it's a very critical if your external oscillator is spoiled, is malfunction. So this means that suddenly your brain is stopped running. So we don't want this to be happen, correct or not? So due to this, PIC24 built in something called fail-safe clock monitor. Okay, let's have a look. So basically, it monitors the operation of the external oscillator and allows the microcontroller to proceed if external oscillator is failed. Okay, means they got something to be backup. So it allows the internal oscillator to take over. Okay, so of course, this one is only applicable if you're using external oscillator, but it's seldom to have an internal oscillator failure. Okay, so normally is wear and tear, the crystal clock that you purchase online, or the crystal clock that you have purchased from your friends. So it might not be permanent. Okay, it might cause problem. You never know. Okay, if you are designs a very critical project, let's say for example you create something like pacemaker. Okay, if pacemaker is, if the crystal clock is failed, it might cause a big problem to the person who use it. Okay, so then he detects to a failed oscillator by comparing the internal and external clock source. In case it takes more than 2 milliseconds for the internal oscillator clock to come, the clock source will be automatically switched. Okay, so this means that when fail-safe clock monitor is switched on, he always do perform a comparison, the external clock and internal clock, so that both is running. If there's a big difference, okay, if there's a big difference in case take more than 2 milliseconds, between the external and internal clock to coming in, so automatically he will perform a switching process. So how the switching process is happening? So the internal oscillator will thereby continue operating, controlled by the bits in the oscon register. So we control by this oscon register. So the bits involved is these few bits, okay, COS, NOS, and as well as the OS1 bit, okay, and the CF bit. So these are the bits that's involved when the fail-safe clock is activated. Okay. So the internal oscillator will therefore continue operating by controlled by the bit oscon register when the OS fail bit of the incon register is set. So this is a interrupt. Okay, when this bit is set, you'll trigger the interrupt. When interrupt is triggered, they will perform a clock switching to the internal clock. Okay, external clock will not be used because it's failed. So automatically it will switch into the internal FRC. Okay. So how this thing is work? So when FCSM is enabled, so this bit is situated in our config register. Let's move to the config register. Still remember, under the config register, we got one very unique bit, which is what we call as this FCKSM, this 2-bit. Okay, so basically, if you enable this 2-bit, let's say it's 1 or don't care, the clock switching or fail-safe clock are disabled. So if you want to enable both the clock switching and fail-safe clock, then you have to set these 2 bits to become 0, 0. By default, is switch off. Okay. Okay. So when FSCSM is enabled, the low power RC internal oscillator will run all the times except during sleep mode lah. So in the event an oscillator failure, the SCM will generate a clock failure trap and will switch the system clock to the internal FRC, as I mentioned just now. So the user will have the option either to attempt to restart the oscillator or execute or control shutdown. So once you know that your system is slowed down, it's all up to you whether it's the failure, is it a permanent failure, or it's just something wrong, with the connections or etc. So he give options. He'll alert the user such that whether you want to restart the oscillator or execute the control shutdown to perform a detailed debug. So the FCSM module will automatically go through these phases. Okay, first, the COSC bit are loaded with 0000. What is COSC bit? COSC bit is loaded with 0000. Okay, so actually, what is 00 is FRC. So currently, let's say currently, now I want to switch to 000 to internal FRC. Okay, let's assume that at the very beginning, actually, is an external oscillator is 011. Once it's failed, it will automatically switch to the 0000. So means the current oscillator is 0000. Okay, so at that time as well, you will inform that the oscillating switching is complete. Okay, and this CF bit, you detect as failure of clock. So this is how these 3 sections are worked together. Okay, let's go back to the slide. Okay. COSC is set to 000, means the internal FRC. CFB is set to 1 to indicate there's a clock failure to inform the user. So OS1 bit will clear, to cancel any pending clock switch to ensure that everything is successfully switched to the internal FRC. So once again, let's come back to this. So those are missed out just now. So first, you set to 0000Y to indicate now we are moving into the internal fast FRC. Okay, once they detect failure, immediately you updated the internal clock by telling that microcontroller is internal fast FRC is taking over. At that time, this CF bit will set to 1 to indicate there's a clock failure. And of course, once it successfully switched over to internal FRC, the oscillator switch is complete. Okay, is it all right? Okay, yes. Any questions so far regarding to the fail-safe clock switching? If no, give me a thumbs up. Okay, let's come back. So any questions so far? Are you confused? Okay, I hope everything is going smoothly. Let's check the participant. Okay, seems like everyone is in. Okay, very good. All of you, very good. So let's move on. So now, once you talk about internal fail-safe clock, we also got something called switching. So let's say you're dealing with IoT devices. In a lot of situations, power is one of the very critical things. Means we don't want our IoT devices suddenly consume a lot of power, consume a lot of battery. The batteries run out easily. So one of the way that is consuming power is the oscillation. Higher the frequency means you consume more power. I believe that all of you know this, from other electronic or electrical subjects. Okay, so that's why PIC24 allow you to have a very unique feature to do a clock switching. So if you think that at that particular program, you need a lower speed, you can switch to the lower speed. If you think that that particular program, we need faster processing time, you can switch to the faster clock, or faster crystal that you need to do. Still remember just now in the clock in this chart, they got so many selections for you. There's so many selection, correct? You see, so many selection. Where is it? See, the red color one out, 1, 2, 3, 4, 5, so many selections for you. So doesn't mean that higher speed is better, because higher speed sometimes it will consume your power. And actually at that moment, you do not actually need such a high speed, to process such a simple task. So that's why PIC24 allow you something called a clock switching. So same, the clock switching is still involve the same special function register, and or involve the COS, COS, the current oscillator selection bit, the new oscillator selection bit. Okay, this is a new one, and then the clock fail detect, no, okay, but we are involved oscillant bit. Okay, so there are a lot of selection for you. The selections are 1, 2, 3, 4, 5, 6, 7. They got 7 different selection for you. Okay, let's look at how this thing is working. And class, remember, clock switching maybe is applied in other microcontroller as well. So please refer to the respective microcontroller. So the system clock source can be switched between an internal and external source. So you are free to switch over actually through the oscillon register. Basically, it's just to help to reduce the power. Okay, so slower oscillator, draw less current. Okay, then a higher speed. So which I told you just now. So during normal operation, probably you need a higher speed. But when the application is less active, slow oscillator is needed instead of a high speed oscillator. So you're allowed to choose between all these oscillator. Okay, you're allowed to select. Okay, so various sleep options are available for very low power, but it's often necessary to maintain continuous operation during sleep. So slower oscillator speed may be all that is required during this sleep mode operation. Okay, so let's see how this thing works. Okay, in order to enable the clock switching, so same, you need to enable this FCKSM1 and FCKSM0 by setting it to 00. Clock switching is enabled. Okay, so basically 01 clock switching is enabled, but the fail-safe clock is disabled. Okay, if you want the fail-safe clock to be enabled, just put it 00. So by default is disabled. Okay, so let's move on how these things is working. Okay, so these are the basic sequence. So first, you read the COSC bit to determine the current oscillator source and perform the unlock sequence. So you need to unlock the oscillon register so that it can allow you to update the current source or the new source. So basically, the unlock sequence is just to protect your programming style. Why? You don't want the user simply change these 2 bits by accident. So therefore, in order to update your clock sequence, you need to perform the unlock sequence. Okay, just for your information. Okay, so basically then we write the appropriate value to the new oscillator control, okay, which is at the bit 8 to 10. Okay, so then we perform the unlock sequence, lock sequence to allow the write, unlock sequence to allow the write to the oscillon register low byte, because we got high and low all right, not because we got COSC and NOSC okay. So then set the oscillate bit to initiate the oscillator switch. So when you set the oscillate switch, means you already start the switching process. Okay. Okay, here are the details, or is what is going on. The clock switching hardware compare the COSC and NOSC to ensure that you are not playing fun, So this is to check, the COSC and NOSC are totally different. Okay, if they are the same, then the clock switch is redundant. Therefore, also you clear automatically and the clock switching is aborted. You cannot switch the same thing, correct or not? Alright or not? So if a very clock switch have initiated, the log and the CF status bit are clear, then we perform the clock switching. Okay, so after the clock switching is successfully, you need to unlock it back. Okay, so class, you might ask, is it necessary to lock and unlock? So if you don't lock and unlock, it's perfectly all right. So lock and unlock sequence actually is to protect, such that in future you don't accidentally, perform a clock switching. If you are not an expert, doing clock switching is very dangerous. Why? Because you don't know which sections is really need to be high and need a high frequency oscillator, which section need to be a low frequency oscillator, unless you are the one who design the whole program. Okay, if you pass to if you receive, this program from your senior, then you need to be very careful. You cannot simply perform a clock switching. Okay, so in order to make things easy, there's a built-in function to allow all this clock switching just by calling the built-in right oscon low or built-in right oscon high. So basically, once I call these two values, you are running this assembly code. So still remember, it perform lock and unlock. Everything is being done in this simple function. Okay, so this is just a library. You call this function, so everything will become very straightforward. Example, how this thing it works. So this is my new clock. This is my old clock. So if I want to change to new clock, I just run this function. Okay, so let's say I built in oscon high 101. So what is 101? What is 101? Oops, I need to go back. Okay, just give me a minute because I need to go back to that particular. I copy this over here so that it's easy, Okay. Okay, so at first is 101. Where is 101? Oscon high. So basically, this is high, this is low. Who is this? How to get rid of these things? Am I blocking? Okay, so something is blocking at up there. So this is oscon high, this is oscon low. So basically, now I want 101. So 101 means what? Where is 101? 101 means it's a low power LPRC. Okay, it's a LPRC. Okay, so 101 is a LPRC. Okay, so I'm performing a new clock switching to the LPRC. How to get rid of these things? Okay, it's disappeared. Okay, so this means this is the LPRC. I want to switch to the low power RC circuit. Okay, just writing high to 101. Then my oscon low, I all with 0x01. So what does it mean by 0x01? Okay, 0x01, this is low, 0, 1. Okay, 0, 1. Okay, 0, 1 means what? I initiate the clock switching. So 0, 1 basically is off 1. I initiate the clock switching. Okay, I initiate the clock switching. Okay, 101. Okay, is it okay, class? So then, while the COSC is not equal to 101, if the COSC is not equal to 101, I didn't perform the switching, it's not being updated, or the OS1 is still 1, the OS1 is still 1 means that after the OS1 is successfully updated, the NOSC, it will set to 0. So I will keep on looping until everything is successfully done. Then I only exit this function. So at that time, the clock is being updated to 101. Okay, I repeat again for the old clock. There is new clock Let's say the old clock is still the same. After I finish doing my new clock, I want to change back to the old clock. Okay, class. The writing style here, and the writing style here is exactly the same. I just give you a 2 version. Okay, some they prefer write the whole thing. If you not prefer to write the whole words, then you just put the underscore here. So I repeat again. Now I want to write OSCON high 0000. Okay, basically refer back to here. Okay, my new actually is 00 is fast FRC. So first is just 000. Sorry, okay, just now it's 101 ma. It's 101 ma, so it's 101. The new oscillator. Okay. Okay, then I initiate the switching process by setting the OS1 equal to 1. Initiate by setting OS1 equal to 1. Okay. Then I'm waiting. I keep waiting until my current OSC is really updated to 10. Really updated to. Sorry, this should be is not equal to 000. There's something wrong here. It's not equal to 000. Okay, it's not equal to 0, not 101. Not equal to 000. Why? Because if I put 00 here, I should update this current become 000. If it's not updated, means I keep on waiting and waiting and waiting. It also can be verified by this bit. If successfully switched, the OS1 bit will automatically set to 0. Okay, that's the reason I put the OR bit here. Okay, sometimes this is faster. After this is being done, then only you will update this COSC. So class, is it okay? Any question from the floor that you are not sure? So this means that after you write these 2 functions, in any section of your program, you think that, oh, this one I want to use internet FRC. Oh, then I just call new clock. Just call that function. Oh, this section I need a faster one. I need old clock because old clock is 8 megahertz 8 megahertz Low, this is 31 kilohertz, is it? Okay. So then I need to switch. You can switch here and there, up to your own preferences. Okay, class. Any questions so far? I hope that you understand what I mean. You just need to call these 2 functions. Okay, just using these 2 functions, built-in OSCON low, OSCON high. So basically, they perform everything for you. Okay. So any questions? Is it clear? Or any question? If clear, give me a thumbs up. Class, make sure that you understand on the spot. If you don't understand, please let me know. Okay. So why instead 0? What? Let me see. What is the purpose to include OSCON? Okay, there's a question from Yap Ying Hao. Okay, so it's why 101. Let's say, for example, if my design, I want to switch to low power LRC here. In this case, let's come back here. Let's say here, I want to update. Let's say example, currently I'm running at 011. I want to update it to 101. What should I do? So I should set the new clock to 101 Okay, I want to use the low power LRC. So this one should be 101. The new one, the current one, let's say is 011. The current one. So by writing this 101, this is at the high bit. This is a high bit, means this is the new one, you know. Remember, this is a NOSC one, NOSC. This is a NOSC. There's my pen. NOSC. Okay, so then I trigger the switching process by setting the OS1 bit equal to 1. Now I just wait, lor. I have to wait. Is it really successfully switched to 101? It's still not. It's still not, means that the current one is still 011. So I have to wait and wait and wait and wait until it's updated to become 101. Or it can be shown, you know, by this OS1 bit. If the OS1 bit is successfully done, it automatically, you know, become 0. The oscillate switching is successfully being done. So that's the reason I put the OR here. So either way, you really, you know, show that the thing is being updated, because sometimes this comes first, sometimes this comes first. Okay, because due to this, there's some delay, you know, in the process of the microcontroller. Okay, is it clear, Ying Hao? A bit blur. Okay, let me clear the screen. Let me clear everything. First, let me clear, because probably this is clear this. Clear. Okay, basically, sometimes you want to perform a clock switching. How to clear over? Okay. Let's assume at the very beginning. Okay, at the very beginning. Now let's run. At the very beginning. This is running at the primary oscillator 011. Assume or internet FRC. This is 0000. Currently is running 000. Now I want to switch it to the low power here. Then I should put this at 101. All right or not? Okay. If you agree with this, now I want currently he running fast FRC. I want it to be switched to the low power RC. If okay, give me a thumbs up. You understand until here? Yeah, Boon Ping, everyone, is it okay? Okay, it's okay lah. So now, how to write the code? So very easy. First, I need to tell the system such that I want to switch to 101. This 101 actually is this 101. High byte is this, you know. High byte is 1, 2, 3, 4, 5, 6, 7, 8. 101 is this 101. Then this one, low byte, all with 01. Low byte, I all with 01. Whatever thing I all, it should become 1. This 01 actually, I want to activate the switching, the OS1. This is low byte, this is high byte. Okay. And while COSC is not equal to 101, this is a COSC. At the very beginning is 000 By right, after switching is occur, this will be replaced by 101 So if not yet done, I keep repeating keep waiting until it's successfully being switched. Or it can be shown, you know, by using this bit. One is to initiate the switching. Once the switching is successfully being done, it will automatically going to 0. When 0, the exit the loop. So this means that the switching process is successfully being done. Okay, so this is very useful. Okay, so is it clear why built-in function put and not OR gate is a OR ma? If I put 0x01 my dear, if you don't put this you put 0x01 means what? Means this, you know. Indirectly, you are changing all this, you know. Are you going to change this? You want to put this all 00001? No ma. You want to OR it. OR means what? When you OR gate means what? Don't care. Whatever he won't affect, you know, he just affect this. Whatever OS1, he all will become 1. Okay, so that's the reason we're using OR. OR is very, very important, you know, all this, you know, OR. This is the OR it. Whatever in this OSCON law, I OR with 0x01. Okay, is it clear, Nicholas? Okay, I hope Nicholas, you say, okay. Okay, let's move on. Okay, let's move on. So, in some note taking, so in PIC24, they got 3 different power saving mode. One is a sleep mode, like you are sleeping now. Sleeping means what? Sleeping means you disable the system clock. And most of the on-chip peripheral that disable system clock, and most of the on-chip peripheral that depends on it. Okay, so this means that you disable almost everything lah. Sleep is the highest level. Deep sleep is even higher level, but they don't have deep sleep in PIC24. Like for ESP32, we got the highest level called deep sleep. But however, in PIC24, we just got sleep only. So sleep, basically, he disabled the system clock and all the on-chip peripheral that is using the system clock. Okay. So idle state, you just disable the CPU. Okay, but the system clock continues to operate. Okay, the system clock still running. Basically, the CPU stop executing instruction, means the CPU stops executing instruction. Okay, so ask yourself, you are sleep mode now or you are idle mode? Is sleep mode very dangerous? You're already missing in action. Idle, I also don't know how to say it. Idle is half lah, probably, but the system clock is still running, still operating. Means your hand is still moving lah, but your brain is already somewhere else Okay, already disabled So those mode is better. It just reduces the system clock frequency. I hope you're copying okay, of the CPU. You need to move your hand, you know, so that you become not so sleepy, but keeps the system clock frequency to the rest of peripherals. Okay, so this means that this dose mode is just reduce the clock frequency only. Okay, so sleep mode is the highest level. Everything is like sleeping Idle mode, the CPU stop executing, but the system clock still operating. This means that it's still getting information. Information still can coming in, you know, through other peripherals. Those is just to reduce the clock frequency of the CPU. CPU is still running, but it's just reduced. Okay. Okay. So let's move on. So any questions so far with these 3 different power saving modes? Because a lot of times, you know, in whether in other microcontroller, you always see these three words: sleep, idle, DOS. So deep sleep actually is even further. Okay, means even further means, you know, like the voltage that's supplied to all the devices is even lower. So that's why deep sleep mode is very risky. You know, to implement this sleep mode is very risky. Why? Because if there's a minor mistake, he will deep sleep forever. Okay, this is not what we want, you know, in an application. Okay. Okay, let's move on. Okay, is there any question from the floor? Can I move on? If reduced frequency, the timer or will delay more? No. Actually, it will start functioning. We'll go through it later. Don't worry. Let's have a look. Let's have a look. Yeah. Ying Hao, I can say that yes, because we reduce it. Definitely, the timer, the frequency coming in. Let's say you're using 8 megahertz. If you reduce it, definitely everything will be changed. All right, in a sleep mode, in this dose mode. Okay, is it all right, Ying Hao? Because the timer is calculation is according to the real FCYC. Let's say you're using 8 megahertz, means you are using the 4 megahertz. Okay, thank you, Ying Hao, for this question. Very good. Okay, let's move on. Okay, so this is a dose mode. So dose mode can allow you to change the frequency. Like example, I got 8 megahertz. I set my dose mode to 0101, meaning you divide by 4 lor. But I don't know why you want to do like that. Okay, of course it depends on situation. So by default, the dose mode is 000, means you don't have any clock division is happen. Okay. Ying Hao, if you want to have fun, you try to reduce it, divide by 4. Let's say if 8 megahertz divide by 4 and divide by 2 again, so it's greatly reduced, then you will become things will become not very accurate, you know, when you do calculation. Okay, is it okay? We also got FRC. This is the pre-scaler, post-scaler, FRC post-scaler. Normally we 0000 okay. Normally it's 00000. Okay, but by default is 001 okay. By default is 001 is divided by 4 megahertz. Okay, for information let's move on. So clock division. So this is to reduce your clock division. I told you already just now, it's just to reduce your CPU clock and reduce your FRC clock. Okay, if you want. Okay, so any questions so far? So again, dose mode actually is to reduce the CPU peripheral clock cycle. So this one is to reduce the your frequency clock cycle. Okay, your frequency. Okay, this is to the CPU. This is to your frequency. Yeah. Okay. So remember, when using FRC, it's not very accurate. I told you earlier, when using crystal clock, crystal frequency is very accurate but not very stable. So that's the reason they got one special function register for you to tune your oscillator frequency. Okay, let's say if this is a 8 megahertz, let's say divided by 2 is 4 megahertz. So he will be not very accurate. By tuning this, by adjusting this, you know, the maximum deviation, minimum deviation, then you can make it more accurate. But how to make it more accurate? So hook into the one of the pin. Okay, one of the pin. I can't remember which pin already. I will let you know later. Then hook into the oscilloscope and check, is it really 4 megahertz? If no, check what is the deviation. Let's say it's 7.9 megahertz. Then you probably you need to increase the frequency by changing the tune 0 until tune 5 bit. Okay, which bit is this? It's over here. Okay, still remember in our config 2, we got one section, one bit, which is this bit. Either it's just the clock output at pin RA3. If you set this at 1, means the pin RA3 is the output of this clock. Okay, so you check. If the frequency is incorrect, then you tune it. Okay, this is needed if in your application timing is very important. Example. Okay, but small changes of thing you might ignore this. But again, it depends on application. Okay, so any questions so far? Any questions so far from the floor? No questions? Let's move on. Of course, you can using PLL to speed up. I told you already just now. Okay. So we're not going to discuss this. The PLL is a phase lock loop. This is more technical. It comes to the analog circuit design. So that's the reason we don't look at it. It's a lot of mathematics involved. Okay. And here are the summary of some of the settings. Okay. So let's say you want to use activate clock monitoring, all these things, you know, these are the bits that are involved. Okay. We already went through all this. Okay. So again, please don't accumulate. Please ask questions if something that you are not so sure. Okay. So I'm not try to avoid it's a wrong. I shouldn't say this. It's depend on application. No. Not try to avoid. I mean, in Utah, we try to avoid using external oscillator because it save your money. Okay, that's what I want to say. Because you want to buy crystal clock, it's very expensive sometimes. Okay. So you want the low power, you have to do all this two-speed startup, clock switching, internal RC oscillator, internal oscillator calibration to ensure that you achieve the low power situation, especially if you are dealing with those IoT devices. Okay, let's come to the internal architecture of PIC24. Okay, so let's go through this before we have a short break. And class, remember one thing. You are so lucky because this round you no need to construct the hardware due to this COVID-19. Okay, so you just run simulation. But you construct hardware every year. A lot of students burn the PIC24 because PIC24 is given, loan it to you. You burn it, you keep quiet, and pass it back to the lab. So then your junior will having difficulty, a lot of situation. Means probably your senior burn it, you go back to the lab, you blow it, then it might be burned, you know. That's why you need to do a lot of debugging and checking to ensure that that particular pin is working. Why is burned? Here is the situation. Okay, class, this is very important. Once you look at these electrical characteristics chart, can you tell me what is the voltage should be given to the microcontroller? Here, you look at this carefully. He said that the I/O pin for analog function, the maximum voltage is 3.3 volt. I/O analog, so this means that remember you're doing ADC. Let's say your variable resistor. So maximum coming in is 3.3 volt. But however, if this is the digital pin, the maximum is 5.5 volt. So I don't know why students can't differentiate analog and digital. Digital means that I can have I can power up something like this. Okay, the switch 5 volt to light up an LED. Okay, like I got a transistor. Okay, I can put it to 5 volt or something like that. Example, and okay, let's say TTL transistor. Okay, so but not as an analog function. So that's why a lot of students come to assignment 1. I also don't know why they want to put 5 volt in there, and then burn. Burn, it doesn't matter. They burn up RA0, they switch to RA1, then burn everything, Then say the microcontroller is not working. Go to the lab and exchange with the lab assistant. Then come back, burn again, and burn again. That is very excited. Okay, so I hope you guys are not connecting 5.5 watt in your assignment 1, although it's a protest simulation. So may I know how many of you using 5.5 watt? Yes or no? If no, just type no. Why so quiet? Yes. Oh no. Okay, no, very good. Okay, so this is something that you need to alert. Okay, it's 5 watt lah, not 5 watt. It depends on the situation when it's digital. Okay, and this one, hold on. Okay, PIC24 got a lot of input-output port. What? Will simulation show even? Of course, no lah. In-house, no. No. Simulation don't know whether it's burned or not. You can put any voltage, it's still working sometime. Okay. Okay, because you have to refer to the data sheets. Okay. Come back to our lecture. So this is basically we have a very limited input-output pin for PIC24 because it's just 28 pin only. So input-output pin is something that is very, very expensive in PIC24. This model, because it's 28 pin, so input-output pin is not many, so it's barely enough sometimes. Okay, so here are some of the input-output lah. Okay. Always remember, we write to the latch, we read from the port. Okay, we write to the latch and we read from the port. Okay, so remember this. Why is like this? So let's have a look. This is what is really going on. A lot of students ask me why you have to read from a latch. So actually, once you open up this microcontroller, my drawing is no good. Let me clean first. Yeah. Okay, I try my best to draw it nicely lah. Okay, we have inside the microcontroller they have a data latch. This is a data latch. It's a Q flip-flop. Data is coming in, and they have an OR gate here. And this one is your trice latch. Q flip-flop. This is your setting. So this you come to the OR gate, okay. And this one is come into here. OR gate OR. And there's a beautiful AND gate here. Okay, this will come to here, and this one come to here. So inside they got a MOSFET because this is a 3.3 watt. It's a MOSFET. Okay, bubble. This is a P-type. I hope that you know what is P-type and N-type because you're already very king, you know, in analog circuit. So this is a P-type. This is an N-type. This is a ground. This is your VCC, and this is your pin. This is outside. More or less it's like this. Okay. Yeah. Hey, where is color? Why can't I change my color? How to change color? Okay. Let's say if I want to treat this situation as an output, your trice normally we set to 0 ma. That's why we write to the latch, you know. We set to 0. When this is 0, this will become 0. This will become 1. Let's say I write a data 0. When 0, this become 1. 1, 0 is 1. This will be off. 1, 1 is 1. This will be on. When I write 0, means that we are writing the ground, means it's 0 as an output because this is off. Okay, I hope it's clear. And on the other way round, change color, change to green. If this is 1, this become 0. When this is 0, 0, this will become 0, this will become on. Okay, when this is 0, this will become off. So that's the reason when you write the 1 to the data latch, your VCC is going out as a 1. Okay. However, when you want to read from the port, let's say something is coming in. I change the color. Yeah. Change the color. Let's change to what color you like. Black now. Okay. When this is 1, this becomes 0. When 0 ends with anything, this will become off. This also off. So that's the reason when you read from a port, actually you directly read, from the port itself. Nothing we do with the latch. So that's the reason if you read from the latch, you might get the wrong data, sometimes. Okay, that's the reason we have to read from the port. And class, remember, this architecture is just proprietary to our beloved microchip only. Like STM32 different, ESP32 no, don't have such thing, got direction. Just a microchip. I don't know who is the engineer when he designed this using micro-win. I believe some of you know micro-win. Okay, when he designed the low level, this is something that they are created. So you have to bear with this design. Okay. So, okay, question from the floor. I hope that I keep this. Yeah, question from the floor. Any questions? Okay, if no questions, I'll give you time to ask. Okay, let's have a short break. Let's stop the recording first. Then we we continue recording after the short break. I give you about 5 minutes. You come back at 1:12. Okay. So while waiting, any questions you'd like to ask? Anything you're not sure regarding to this design? So can you repeat on the part that the input of tries slash can change to 0 to 1? No, the tries is okay. Boon Ping. The tries actually. You see when the tries change to 0 to 1. 1, this is 1. This is 0. 1, 0. Let's say the data is 1. Okay. Okay. So let's say put don't care here. Don't care all with 1 is always 1. This will be off. Off. 0 with don't care is always 0. End gate so this is 0. This is off also. So this means that basically these two P and N MOSFET is off during the input time. So that's why we don't look at this at all. So disable. So that's the reason when you read something externally, we directly read from the port, coming in. I press the button, switch button is 1, I detect 1. They will store in the register, some register. Okay, is it okay, Boon Ping? Okay, Jing Sing, for lab 2 conclusion, do we need to show our result? Jing Sing, you show the result. Actually you will give me, you will submit the Proteus file, I will run it. Okay, but during the demo sections you have to show me. I will ask a few questions regarding to your result. Is it okay, Cheng Zeng? Okay, and remember class, basically I don't bother about what is the final output. My order is about how to do a proper debugging using Proteus and know how to use the watch window, breakpoint, all these things, and you're able to produce a readable, professional coding, with a proper documentation. That's what I want to see. Okay, I don't want it work perfectly, but you simply write here, write there, very messy. I don't want to see this. I want you to have cultivate a culture to write professional programming, a professional program, in embedded system design. Okay. Okay, we will continue. Start recording. Okay, everyone is back. If everyone is back, give me a thumbs up. Only one. Let's call someone. So make sure that they are here. Sim Zing Wei. Who is Sim Zing Wei? Is Sim Zing Wei here? Sim Zing Wei absent today. Let's download the attendance first. Who is Sim Zing Wei? Oh, here. Okay, and is it okay, Zing Wei? Everything okay? Hu Kai here. Okay, very good. Okay, let's yeah, my advisee, Yong An. Mr. Leong Yong An, are you in? I thought you are missing. Okay, Yong An, I want to catch up with you. Okay, don't leave. I mean, I will catch up with you after this, after the class. Okay. Let's continue. Okay, I'm going very, very slow. Okay, so I cut and paste this just now. I put it over here. I'm lazy to draw. Okay, so in the situations in PIC 24, they got one very interesting situation. Is what we call that is an open drain. Okay, open drain is controlled by special function register, or you can control by the pin called ODCX. No, 0 means RB0, 1, 2 lah. So when ODCX is equal to 1, means the open drain is activated. When open drain is activated, this is being disabled. I forgot to draw here. Disable. So it's disabled. There's no more pull up here. No more. No more. We just left this. Okay, just left this without the pull up resistor. So this is very useful when you come to I2C communication in future. Okay. Why this is interesting? When they don't have pull up, so this means that this is when this activates is always just grounded. So that's the reason. Let's say this is a 2 microcontroller 1, microcontroller 2, and I want to communicate this together. I link this together. When you link this together, you need to have a pull up over here. So in this situation, the connection here is a AND gate. It's an AND gate. Why I can say this is an AND gate? Okay, you trace it yourself. Let's say trace is the output Trace is the output. When the data is 0, 0. When the data is 0, 0 here, 0 here, the output, you measure this port I measure this this will give you 0. When 0, 1, this will give you 0. When 1, 0, this will give you 0. When 1, 1, then only give 1. If you construct the circuit like this, by activate the open drain. Open drain means we disable the P MOSFET. You disable this. Okay. So when disable this and put it as an output, when the data is 0 here, when the data is 0 here, then the output should give you 0. Okay, when the data is either 0, 1 here, it will give you 0 and 0. Okay, why 0? Because we always activate this, correct or not? Unless this is 1, 1, this is 1, 1, this will be off actually. Okay, then only you detect 1. Okay, is it clear, class? This is what we call an open drain, or in other words, we name it as wire end. Wire end. Okay, you go back and trace it yourself. Is it okay? If okay, give me a thumbs up. Is it okay? Yokim, is it okay? Okay, who is not okay? No, just switch on the mic. I want to ensure everything is okay. So, so that you save your time. No need to watch the video again and again and again and again. Okay. Okay, let's move on. I will give you this slide. I will redraw it nicely. I will post it, but you better draw it now. I give you some time to draw it. Can you draw it? Can you draw it? Okay, on the piece of paper that you have prepared. I asked you to prepare. There's no MOSFET here. The P type is disabled. We just have N type. So whenever input is 0, 0, output is 0. Can you just draw this? I give you 3 minutes to draw this. Do some work. Okay, so that when you draw, you try to understand, or probably try to debug what I told you just now is really true. Okay. If I put 1 here, what happened? This becomes 0. This will become 1. Okay. This is 0. 0, 1, this is off. Okay. So same here. This will become, if this is 0, if the input is 0 here, this will become on. So we share the same ground. So whatever we listen here, measure here, you go to the ground. So that's the reason it's all 0. Okay. So have you drawn this? Okay, I give you another 2 more minutes to draw this. So do some work, rather it's so boring, you know, listen to my lecture. Okay, shall we move? Okay. So yeah, you have, if you draw this, give me a thumbs up. Have you drew this? If yes, give me a thumbs up. Why are you still busy drawing? Okay, just one. Okay, please, I give you some time. Junquan, are you there? Yep, Junquan, are you there? Junquan is not here. Yep, Junquan. Where is Junquan? Absent. Looks like Junquan is absent. Yeah, Junquan, yes. Is it okay? Everything okay? Have you drawn this diagram? Okay, good. Okay. So probably in class, remember this Friday, okay, I purposely arranged such that start from 9:30 until 12 o'clock is for you to ask questions, you know, regarding to my lecture and regarding to the assignment. If you got any problem, just come. It's not official because you know lab ma, right? I can always put in, you know, you can always ask questions, okay? And also, so the top is the latch for output and the bottom is the, no lah, the bottom is tries. Why got output? This tries. This is data latch. Junkit, this is the both also latch. This is data latch. This is tries latch. Still remember the position? Where's my pen? Latch. Okay, this Friday, if everyone is okay, let me know if it's not okay. 4 o'clock, start from 4 o'clock, we try to use ESP32 on the spot. You know, please be ready with ESP32. And most important is the cable that connects to your ESP32. Make sure that it's a data cable. Still remember USB cable? It's not a USB type C, you know. Please check. You got, make sure they got that cable, and that cable is a data cable. It's not the power cable. If a power cable, your ESP32 won't work one. So I want to start ESP32 this Thursday so that you can play around with it, because ESP32 is not difficult at all. So once you familiar ESP32, you can play a lot of things. Then we move to real-time operating system, FreeRTOS and ESP32. Then we go to the IoT. Okay, so this Thursday, I want to ensure everyone have the ESP32. I hope that is okay. It's 4 o'clock. Is it okay? Is it okay? If not okay, let me know, you know. If not okay, just say not okay. Okay, so we try ESP32. Yeah. Yes, Thursday 4 p.m. You can't make it, is it, Yinghao? If you can't make it, I can reschedule. No, this is not official class. ESP32, the internal structure, all these things are not in the exam one. This is just a private lecture with all of you. Okay. Okay. So ESP32 is okay. It's not in the internal architecture, all this programming. I'm not going to ask you Android programming. The Arduino programming in the exam. No. I just want you to play with ESP32. Is something that is quite interesting, correct or not? Okay, let's move on. Okay, so so I update with you. Seng Chen, no problem. You don't need a component. You just need the ESP32. That's all. No need component, no need LED. Even I give you a code, I just make sure that everyone can program. Use your ESP32 is alive. Familiarize with ESP32 only. It's nothing big, Okay. Okay, class. Let's come back to this. Okay. Actually, there's a certain way of writing in C. Like here, set the 8 bit of port P to output and lower 8 bits to be input. Then you can set tries equal to 0, 0 FF. Okay, you can do something like this. Okay, so if you prefer not to change any bit, you should use or AND. Okay, these two are beautiful symbol. Okay, like drive RB15, RB high, others low, then you can do some setting like this. Okay, this is a way of writing. Okay, like wait for RB0 is high, then you can write something like this. Okay. Okay, or you can just write RB0. Okay, or same like, or you can write like while RB0 equal to high, then do nothing or something like that. Okay, this is a way of writing C programming. I'm not going through in details. Same with this as well. This is just to explain to you why latch and port, there are a big difference. So remember, we read from the port, we write to the latch. Okay. So, and this is some of the C programming is the same. These two is the same thing. Okay, same. Means this is always true. When RB equal to 0, then you do nothing. You keep on looping lah. So it's same. While not equal to RB2. While RB is not true. So this is always true. This become not true. Okay. So this is the same thing. The writing, the C programming writing only. Okay, let's move on. Same with this. So in a lot of situations, they are not advised you to do these two things at the same time. If the frequency of your microcontroller is very high, you should give them a resting time, a delay, a short delay here. Okay, but however, in your situation, it's not a problem. Why? Because your code is not optimized. Once you convert into assembly program, there's a lot of things over here that will give you a delay. If your code is optimized and your speed of your microcontroller is super high, like 64 megahertz or etc., then the programmer, the datasheet advise you, don't do something like this, because he might miss, he might miss this. Is too fast. When too fast, you might miss this. Okay, just to share with you only. So, but in your situation, it's not a problem. Okay, Okay. So the Smith trigger to smoothen your design, your input buffer. This is no problem on these circuits. Okay, analog and digital, I told you already. So you need to make sure that analog is disabled by using this individual bit or using this special function register, or else your digital is not working. It's worse. You don't do this. By right is analog, then you connect to the LED. Burner. You put 5 watt burner. Sorry, burner. Actually, you want to do it as a digital, but by default, it's set as analog. Then you don't realize this. You activate this. Then in real world, in hardware, it might burn. 5 watt, you activate analog maximum is 3.3 volt only. You burn what? You burn the MOSFET law. Okay, probably lah. Okay, if this is set as an input, some more worse. Okay. Okay. So, and one more thing is this. This is a beauty of PIC24. When you're looking at the datasheet of PIC24 and the very first page of the electrical characteristics, you can see something like this. He said that I can sunk the current 25 milliamp I can source the current of 25 milliamp. Maximum, this is maximum, okay, all maximum, maximum for all the port is 200 milliamp. This means what? So in your design, you always connect like this. You always connect like this. May I know which one is working? Yes. Anyone from the floor? Just type A, B, C, both also working. D, both also not working. Not working, not working. Just type which one is working, which one is not working. Or both also working. D, both also not working. Yes, from the floor. Come on, please participate on this. Okay, Sing Ching say A. Yeah, come on. I need more answer. A, C, 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 C. Looks like. Okay, some more. C, 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 C. Some more. That's all. Jun Chuan, all these people didn't join. Of course, seems like more C. Yes, congratulations. The answer is C. Okay, so of course, it depends on the LED. So this 25 milliamp is definitely enough. The typical value of LED is just 10 milliamp only, so no problem. So like this also no problem. I can sing and sung the current is no problem. This directly give enough current to light LED. So both is working. Okay, but remember, if you ask me this one or this one, I will prefer this one. I will prefer this one. Why? The answer will review in future. Okay, when it come to the more details, I will prefer this one. Okay, I will prefer this one. Okay, let's move on. So open drain, I already explained it to you. Okay, enable the open drain and internal weak pull up, CN2 PUE, I told you already. So that's why this one is to save your resistor. Okay, because you can activate internal weak pull up. It's just like your assignment 1. You don't even need to connect your switch. Let's say your switch, you need a pull up resistor, correct? You don't need this if you enable the internal weak pull up CN2 PUE. Okay, let's say this pin 2. Okay. Okay, another class. So this one is save money. Why? Because you are enable the internal weak pull up. Okay, rather than you are using the external pull up, your circuit look more messy to use up more PCB space. Okay, so that's why you can enable pull up resistor in order to save money, save the PCB board. Okay. Okay, then we come to something that is even more interesting called PPS, peripheral pin select. Okay. So what is this PPS? So for your information, PIC24 has a very limited pin, only 28 pin. Okay. So actually, sometimes in some situation, some of the function is not to be seen in this scheme pin out. Like for example, where is the if I want to do with UART, where is the transmit? Where is the receive? Where is the interrupt 1? I want to have interrupt 2. Can you find that? you are not able to locate all these 4 very important pins. Okay, so but however, these 4 pins actually exist by configuring the RP pin, what I call a remapping pin. So these are the one of the beauty of PIC24. So this means I can assign RP15 to be transmit over here. I can assign RP1 transmit to be here. I can assign RP7 to be here. Or I can assign INT1 to be here. I can assign INT1 to be here. Okay, so this is very great, very good. Why? Let's say you have designed a PCB board. Okay, you have solder your microcontroller into the PCB board. So suddenly after 2 years, you want to do upgrading. When you do want to upgrading, I need the interrupt pin. So the interrupt pin here already blocked by capacitor or some other component. So that's why, oh, no problem. Here is still got some empty space. I can assign this RP0 as an interrupt 1. So is it okay? This is what we call a remapping pin. So most of the pin can be remapped like UART, SPI, and I2C over here, or this one. Some of the pin already existed. Those are not to be remapped. You already started in this pin out. Okay, those can be remapped. I can show you later through a few tables. Okay, so any questions until now regarding to the remapping pin class? Any questions? Remapping pin? If no question, just say no. This is very important. Also quiet. Is it so far okay, class? Remapping pin? Okay, so class, the following is very important. Let's see how we deal with the remapping pin. Okay. I'm not going through all these things. I'm not going to read this. What are the advantage of remapping pin? Definitely, there's a lot of advantage. You provide designer with exact peripheral set you need. Okay, and it minimize the package size. Of course, since you got remapping pin, the package of your microcontroller can be very small, 28 pin only. Reduce the software complexity. Okay, you don't need to do a lot of configuration, the software complexity through increase the hardware functionality. Optimize the pin layout, we reduce the design time, board complexity, electromagnetic interference. Let's say, for example, you're using 40 pin, 50 pin, 128 pins, it might introduce the electromagnetic interference. That's why you need an additional circuit. Okay, just like a ESP32. So like ESP32, when they design the microcontroller, you have to build in the electromagnetic shield into it. Okay, so let's look at how you want to configure this remapping pin. So there's a certain process again. You have to, this process is like this: unlock and lock. Okay, class again. Do you remember just now we got unlock and lock? We got an unlock pin and lock pin. So again, unlock and lock is just for safety purpose. If you don't do unlock and lock, it's perfectly all right. Okay, they got 2 ways to do unlock and locking. PIC24 give a double security on this feature because it's so worried such that, as I told you just now, I give you this project, I pass, your senior project to you, and you're not sure what is unlock and lock, you might make a terrible mistake. So that's the reason they got unlock and lock to protect your pin assignment. Okay, so the unlock and lock process can be done through config register. Okay, here, I hope you're following. This one. This one, IOLI way. So if you put 0 here, your OSCON bit IOL lock, okay, can be set freely. So once you put this as a 0, I can control, unlock, and lock through the OSCON register under the IO lock bit. Whereas if you put this as 1, means you only allowed to use IOI locker once only. Other than that, you unlock using OSCON register under the IOI lock, you are not allowed to do so. So you need to keep on change your config register IOI way, to become 0 in order to perform unlock. So basically, to summarize, IOL way, if you set it to 1, is like a GIE, the interrupt master lock. This is a master lock. Okay, so once you enable IOL way become 0, you are allowed to lock and unlock using software by configure the OSCON register. Okay, let's move on. So here are the process, but no worry, we can. There has a special way to do it. How to do it? Okay, by calling a built-in function like what we did just now for the clock switching process. So the IOI lock is over here. Here, our lock is active and not active. This one, input output IOI lock. Okay, is it okay or not, class? Okay, let's play with the system. Okay, so unlock. You are not going to type this. Class, is perfectly all right. If you want to type using assembly code, you can type this off, move OSCON. But however, this code can be simplified by calling this built-in function. Okay. Do you know why I end with 0xBF? Let's say the OSCON low bit is 1, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. Okay. Now I want to unlock this. Unlock means what? I just want to. Set this bit become 0. Okay. Which bit is this? Bit number 0, 1, 2, 3, 4, 5. Bit number 6. So it's this bit. So this bit. So without changing all this. So while I perform the AND gate, this become don't care. This no matter is 0, don't care. Okay. Now is your job. If I want, this is lock. This is unlock. If I want to lock, what should be the value here? Yes. Come on. Give me the answer. If I want to perform locking, what should be the value here? Without changing other bits. What FF? Why FF? Unlock. Lock. This is unlock. Unlock this bit should be 0. If you want to lock, this bit should be 1. So what should be the value there? Yes, Ying Hao. Very good. Of course, it should be excellent. It should be all with 0x40 lah. All ma. Why all? I just want this bit to be 1. All right. Then all lah. If I all get with 4 0 0 0 0 0 0, all get all. If all, don't care. No matter is 1, don't care, don't care, don't care, don't care. Okay? So it's quite straightforward, am I right? Okay, take Sheng Chen, very good. It's an all get. Okay. So good try for Wing Bin. Okay. Yeah, okay. So class, but this is not our issue. This one you just call the function. But how about if you want to assign that bin to become an input? Let's look at this clearly, class. Look at this. I want to assign receive to RP0. Means the RP0. Where's RP0? I can't see. Oh, yeah. The RP0, this bin. I want to assign this bin to become a receive. Receive means it's an input lah. Okay. And I want to set RP1 to clear to send. It's an input as well. RP1, the RP1 here. I want to say clear to send. Both clear to send and receive is an input. So how to assign it? After you unlock it, you have to refer to the very unique table. This table, we look at the input and identify their respective reserved word. Let's say just now is transmit. Sorry, receive, is it? Receive, just now is receive, receive. So just refer to here, receive U1 RXR and the clear to send U1 CTSR. Just type like this. Class, remember? So just underscore U1 RXR 0. 0 I remap to the pin RP0. 1 I want to remap to the pin RP1. Once I execute these two lines means RP0 or automatically become receive. RP1 automatically become the function of clear to send. Okay, you may type like this or type like underscore U1 RXR. Okay, like this one actually is just underscore U1 CTSR equal to 1. Okay, so this means that we remap pin 1 to clear to send, which is an input. Okay, class. For output is a bit different. Beware. Beware. So if I want to set the RP2 output now, output RP2 to transmit. This RP2 I want to transmit. Transmit is the output. So the difference is like this. You have to refer to the table again. This is the output table. Transmit is number 3. You don't care about the reserved word, you know. The output is number 3. So this is how we write it. Underscore RP XR number 3. This X is which remapping pin you want to map to. Is 2. Then it's 2 Put 2 over here. RP2R. So the way of remap input and the way of remap output is totally different. Okay, I hope you know what I mean. Okay. So I repeat, for receive, get the reserved word. These are the remapping pin, RP0. For the output, identify the remapping pin. This is RP2. These are the value you need to find in the table. This is in the table, the reserved word. So there's a difference between input and output. So after you remap, you need to lock and unlock it. Okay. So is it clear? So I give 2 minutes for you to digest. So this table is always given in the exam. Okay, if you are sit in the hall lah. But however, if this is like an open assessment, this question won't appear because you can get it anywhere. But it's very important, you know, when you design your Pick 24, okay, for the final assignment. Okay, you probably need a lot of pin remapping. Okay, like those that, you know, one of the reason I don't want to ask you to use external interrupt, because if you want to use a lot of external interrupt, you need to do a lot of remapping pin, and moreover, I haven't teach you remapping pin. So now I taught you remapping pin. Maybe you can using an external interrupt if you want, but I still not recommend. So it's up to you. Okay. So class, any questions so far? Okay, please post your concern over here. Yes. Like, let's try again. Let's say I want to remap request to send. Request to send is an output. Output ma, I request to send my output ma. I send a signal out ma. So I want to remap to RP3. So you have to go to the table. Not this one. Output. Where is the request to send? Request to send is this one, number 4. Okay. Remember, it's number 4. Go back to our program. So it's number 4. But however, you want to remap to the RP3, so it's underscore RP3 number 4. Okay, number 4. This is the pin that we want to remap to. Okay, how many functions that we allowed to remap for the input? Here are all that we can remap. External interrupt 1, external interrupt 2. For output, this is all the function we are allowed to remap. Output compare, SPI pin. Okay. So is it okay, class? If okay, then this means that so here are the, again, reminder, make sure that you understand what is going on. So we end our, tentatively, we end our chapter 3. We come back to this later. So this Friday, we will try to finish the analog digital converter, and we start real-time operating system next week in order to catch the assignment lab 2. So I have to do a bit of swapping, as I still remember, if I put real-time operating system at near end of August, you are all in trouble in doing my assignment. So that's why we'll kickstart the real-time operating system lab, you know, in the coming lab sections, and we will start real-time operating system. We come back to this later, this input-output section. Okay, so we still got 5 minutes. Within these 5 minutes, I just would like to ask you a few questions on it. Okay, so I want all of you participate over here. Okay, let's say, so all of you listen carefully. Let's say one day you're being assigned to do to use analog digital converter, and your senior engineer told you that the analog digital converter that used in the Pick 24 is not very suitable. You are asked to purchase additional analog digital converter as an IC, as a chip. So before purchasing, other than size and price, what questions you going to ask? What question you are very concerning about before you purchasing this analog digital converter external chip external IC. So basically, you know that analog digital converter actually is to convert those external analog measurement like temperature, pressure, light, okay? And with the help of your sensor or transducer, you need a signal conditioning circuit. Sensor normally it's everything is built in, okay? So then only you can go to the microcontroller by relying, on the analog digital converter. Here are some of the analog digital converter, the popular one, okay? Like what you measure outside, measure temperature, it come in milliamp. What is taking up in the microcontroller? 0.3.3 volt. If this is a negative milliamp to positive milliamp, you need a signal conditioning circuit to convert it in the range of 0 to 3.3 volt, okay? Such that it can accept by the microcontroller. So this is done by the signal conditioning circuit. Signal conditioning circuit normally it just consists of an op-amp with some resistors, okay? We'll go through this later. Okay, now come back to the question. Can you tell me what things you're going to ask? Yes, start from the attendance list first. Yeah, while waiting, Ang Xiang Long. Yes, you can using the built-in ADC. It's not a problem. I said that if your senior engineer said that built-in ADC is not functioning. Ang Xiang Long, if you're asked to purchase an ADC, I believe that you already learned ADC before, in microprocessor, in other subject as well. So what you always ask, probably ask the senior engineer. Okay. So, okay, I give you a first question. I give you a first answer. First, you might ask, what is the input? Is it the input in current? Is it input in voltage? If you're in current, your ADC just accept voltage, then you need to do a bit of conversion. Am I right? So this is my first question. Okay, first question I was going to ask. Yeah, Xiang Long, can you give me one answer other than cost and size? Ang Xiang Long is absent, is it? Or you're purposely waiting until 2 o'clock? Okay, Ang Xiang Long absent. Where's Ang Xiang Long? Okay, extra component need to buy to fulfill it. Wow, such a very standard answer. What extra component to buy? Okay lah. Okay, I accept that probably the ADC need the external component to make it run, probably additional resistor and capacitor. Okay, I accept your answer. So next, Sirin Fong. Sirin Fong. Where is Sirin? Is this Fong Min Li? Yes. What question you gonna ask? Yes. What question you gonna ask? They got a lot, They got a lot of reasons why. What question you gonna ask? Yes. Okay, I give you one more answer. Okay. Number of pin. The ADC channel, the ADC input channel, how many pin? How many channel? Is it 8 channel input? You can have connect to 10 sensor or 8 sensor or something. The number of pins that are available in that particular ADC, that is one of the requirement. Okay, I think it's 1:59. Each of you go back and think what question you're going to ask before you selecting an ADC. I'm going to ask you next week, and not next week, this coming Friday. Okay, this is very important. Boon Ping, very good. Okay, Boon Ping, resolution. Whether it's 8-bit ADC, 10-bit ADC, 12-bit ADC, or 16-bit ADC. Like for example, I want to use ADC to measure what? Measure the drugs. Still remember, drug trafficking in Malaysia is very serious. One is more than 1 gram. I'm going to hang you, correct? you're going to being hanged. Okay, so in this case, ADC is very, very important. So if I'm choosing 8-bit, 8-bit cannot measure until 0 to 5 watt. Why? Because 255 divided by 256 times your 5 watt is actually 4.98 watt only, your V reference. So maximum is 4.98 watt, but due to 0.02 watt, I might kill someone, you know. So that's why you go for 10 watt. Okay, so accuracy is a resolution. Okay, I think that's all. Okay, thanks for listening. So I will stay back here. So any question you can always ask. Okay, we try to make this subject as interesting as possible. So in class, I will draft a summary of chapter 3, lecture 3 just now. Please go through it and make sure that you understand on the spot. Don't bring all these things back, you know. Okay. So I will stop recording and then see you this Thursday. And remember, this Thursday morning 9:30 is if you got doubts, if you got additional question to ask me, or you are not sure about the final assessment, you can always chat with me this Thursday morning. Okay, through the lectures group to the lecture group, not the lab group to the lecture group. Okay, other questions?